Leman. Leman. Yeah. As a quick update before we start, that address is not going to work because for some reason Hilton Wi-Fi does not go to CMU servers. So if you put a number 2 at the end of that address, it'll redirect you to a different server that's not CMU that will get you all the slides and things. They're pretty large, and so it'll probably take you the entire 3 hours to download the slides, so you might want to wait and just watch them, but if you want to get to it, they're there too. Yeah. Sorry. I'll say that, and then I think whenever we have one of those breakpoints, just be like, and just be like, hey, we're gonna start this other thing and questions what we just did. Hmm? Should we start? Yeah. All right, let's get started, I guess. It's around 9. Hey, everyone. My name's Alex. I'm a graduate student at CMU. This is a tutorial with Leman Akoglu, professor at Stony Brook, and Christos Faloutsos, professor at CMU. So I'll just do the introduction first, then I'll hand it over. So the slides, as I mentioned before, aren't accessible from this link because CMU's servers aren't working from Wi-Fi here. So to put a 2 at the end of the URL, you can get to the website. So this is covering graph-based user behavior modeling from prediction to fraud detection. First, I want to thank, of course, all of the great agencies that have helped make this research possible. And so when I say graph-based user behavior, what it means is we can often handle many different types of data from the internet in particular, but overall in the world around us in graph formats. So we consider sort of this classic Netflix picture of users and they rate some movies online. We might want to say there are 3 main questions. First, how can we sort of understand typical or normal behavior, maybe the preferences of individual users? How can we find suspicious users? And really, ultimately, how can we distinguish these different groups of behavior and preferences? And there's a wide variety of sort of different graph types we'll look at over the course of this tutorial. We have undirected graphs. Sort of Facebook is the classic example, but also LinkedIn, DBLP, let's say co-authorship. Directed graphs, so Twitter, who follows whom. Instagram, Google+, Tencent, Weibo in China, Tumblr. We can have bipartite graphs, which is, let's say, users and the pages they like on Facebook, or YouTube, the channels you follow, GitHub, the repositories you follow. And you might therefore know some node attributes about those people, let's say, and how does that inform which pages they connect to? So we know what college you went to. We might know edge attributes, like the time that the edge was created, or as before, the rating on that edge, which is, of course, on all these rating sites is valuable information. We might also know text on top of that. Sort of maybe say it's an amazing product with 5 stars or a waste. And we also might know actually ahead of time that some nodes in the graph are suspicious or fraudulent. And we might try to therefore do the semi-supervised problem of figuring out what other nodes are, let's say, honest or fraudulent. And so really we have this cross product of different properties we're going to try to address here. There's the type of graph. There's do we have node attributes and what are they? Do we have edge attributes and what are they? And do we have an unsupervised problem or a semi-supervised problem? And we're going to look at sort of the cross product of all 4 of these things. We can view it often in matrix form. This is sort of a quick sort of aside on this, is that we'll sometimes move between graph form and its matrix representation, where an edge is represented by either the value, a binary 1 or 0 in the graph, or maybe the value on that edge is represented as, let's say, the 5 stars and missing values in the matrix. We have a tensor, let's say a 3-dimensional matrix, essentially, where you say we have the time that edge was created is your 3rd mode of the tensor. And we have a bunch of tasks we might want to sort of, given this data, might want to accomplish. So can we predict an edge that doesn't exist? Do we believe it should be there? We want to predict node attributes or edge attributes given those node attributes. Like, are these people in a relationship? Are they, do they go to the same school? The Netflix problem says if there is an edge, what would the rating be on that edge? And we want to find sort of frequent item sets or groups that seem to act together in this community fashion. And ultimately then, again, fraud detection. We want to sort of be able to know when there's some sort of odd anomalous behavior that we want to sort of isolate, detect, because it can generally deceive users and mess up our other algorithms. And so this is, I think, one of the key things about this tutorial was we're trying to explain is the relationship between these different problems, and in particular between modeling normal behavior, typical behavior, and anomalies, and how they are really just 2 sides of the same coin, and viewing them jointly is useful. So in this picture here, I might say, okay, we have this general form of, let's say, this rough model of normal, and this thing out there is an outlier. You might have more fine-grained models. There's really these 2 clusters in this model, and we might get these are on the periphery of those clusters. We might get an even more fine-grained model, more complex, where we'll have maybe 3 different clusters. We find this one is really small variance. This micro cluster is suspicious and kind of weird. And you might actually say we know ahead of time from some domain expert that this sort of elongated shape, this elongated cluster, that's the really fraudulent pattern, even if it's not necessarily as outlierish as the other ones. And so these different ways in which the normal behavior and the abnormal behavior can relate to each other, and different approaches that you can use sort of to, given one method, to sort of understand the other. So we're going to go through 3 main techniques over the course of this talk. The first is going to be local subgraph analysis, which Leman will present, followed by global propagation methods through the graph, and finally latent factor models and spectral methods. For all 3, we'll go over the background, sort of to get you up to speed on what we mean by this, sort of the base material, the techniques, followed by sort of the way they can be used for some of these normal problems I just mentioned, predictions, things like that, and then ultimately how they can be used to sort of understand anomalies, outliers, and fraud. Really, we want to sort of make this as useful as possible. So if you have any questions, feel free to just throw your hand up, and we'll try to every so often ask people. But yeah, at this point, I'll hand it over to Leman.
Good morning, everyone. So I'm going to talk about subgraph analysis and how to find subgraph patterns in large graphs as well as anomalies. So this will follow this template. So let's start with some background. What's a subgraph? Given a graph, a subgraph is really a subset of nodes and the edges between them induced by these nodes. For example, some subgraphs of interest could be the dense subgraphs, the largest, densest subgraph. And here you can represent density as greatest average degree or edge density and so on. Another subgraph that is well studied is ego networks. The definition is an ego network is a node, all its neighbors, and all the connections among them. Other subgraphs could be triangles or, for example, here you can find, given a pattern, like a triangle pattern, you may find matches of it in a graph. You see three matches of a triangle here. The pattern could be a clique of 4, right? So you may be interested in finding those matches in a graph. And subgraph in general is nodes and edges induced by them, right? So we can represent graphs as matrices, and subgraphs here could be some subset, small, dense areas here inside the matrix. So you can think of it as a tile of dense ones inside this large sparse matrix. And this may correspond in a non-square matrix. Maybe these are users and these are pages with like relationship. This could be, this corresponds to a near bipartite core, right? So there's this representation equality between the matrix and the subgraph. And you may be interested in rearranging your rows and columns of the adjacency matrix in a smart way so that the patterns show up like this. There are a lot of dense cliques and dense bipartite cores and other sparse areas. Okay, so this is called co-clustering or cross-associations. Okay, so that's it for background. So let's look at how to find normal behavior through subgraph analysis. We'll start with oddball, with egonet patterns. So remember that egonet is a node, all its neighbors, and all the connections among them. So that's the definition of what an egonet is, and it's a well-defined subgraph. So given a very large graph like this, you may ask the question, what kind of patterns do the ego networks follow? So we want to go from this large mess to something more structured. And the question is, maybe I want to study some properties of these ego networks, but what should these properties be so that I observe some pattern as well as maybe spot some outliers? So in the study, we looked at several properties of these ego networks, like number of neighbors, number of edges in the ego net, the principal eigenvalue, and so on. So in order to better understand, we studied them in pairs. So we are going to look at some scatter plots like this, and we found some strong correlations among several pairs of features. So here you're seeing number of edges and number of nodes in the ego net for each node. So each green dot here is a ego net represented by the node or the ego inside the graph. And you see that there's a strong correlation between number of neighbors and number of edges. So the more neighbors, the more edges, superlinearly. This is log-log scales. And there's an upper bound and lower bound. So this is full star with slope 1. And full clique is slope 2. So in real graphs, the pattern is somewhere in between. The correlation is somewhere in between. You can look at other pairs of features. For instance, number of edges versus total weight. Right here again, we see that we can find patterns of fit that shows strong correlation between these two. And another pair of features is total weight and the largest eigenvalue. Here again, there's a lower and upper bound. So if all the edge weights in the ego network are the same, then you will see that the ego net will fall on this line with slope half. And if there is only one edge or a very dominant weighted edge, then it will fall on the slope 1. And in real graphs, everything is somewhere in between. So here, again, the green dots are the ego networks, and there are millions of them in a graph. So these are the patterns of ego networks. So from ego nets patterns, I'm going to move to role discovery. So other thing you can ask is, can I study subgraphs to find roles in a graph? And you can. So the way to do it is Henderson et al. Define some useful node features. Here, following from earlier work, you can define egonet features, nodes in the egonet, edges in the egonet, density, and so on. But they also extended it to recursive features. So once you know the features of your neighbors, you can define mode, max, or mean over your neighbors, and you can do this iteratively. So you can construct this long list of recursive features. And then, given these, you can learn classifiers to predict node labels. In the supervised case, you have the graph, you have the nodes, you have labels for them. So let's say there are 4 Ws, 1D, 1P, right? These are representations of roles. Then using these recursive structural features extracted from the neighborhood or subgraphs, right? We can learn classifiers to label unknown nodes in a different graph or in the same graph. Here are some example results. Here you're seeing some training instances of 3 different ego nets of 3 different roles, right? And then these are the test instances. And I'm going to show you some classification results that shows that using structural recursive features that comes from these ego networks and subgraph features, you can do a pretty good job in recovering these roles or predicting these roles. So here we have 2 types of graphs, A and B. This is showing learning on A1 and predicting on A2. So this is within network classification. The results are really large for regional features, which are the recursive ones. And you can even do transfer classification. I train on A graphs and predict on B graphs. So you can also predict roles in other graphs. So features are very general to generalize over different graphs. Okay. Here are some examples to these roles. You are seeing a network psi. So each node is a researcher, and this is a collaboration network of network scientists. And we found here 4 types of roles. The blue nodes here form dense cliques. For instance, Christos and Andrei Broder, they belong to dense cliques of big blue dense subgraphs. The red nodes are bridge-like, so they connect other communities to each other. The majority of the nodes, we call them background or mainstream, are the gray nodes, right? And then there are these like elongated chain-like clusters, like the green ones. Okay, so we found 4 roles here using this study. Okay. Continuing with EgoNets and trying to model user behavior, Ugander and Backstrom, they looked at the user engagement versus the number of connected components in the EgoNet. So you have this user here. These are all its neighbors. And then you can ignore these edges and just find connected components of the neighbors. And then here you're seeing the engagement versus the number of components for different sizes. So let's just look at the black curve. This is for all the components. It shows that the more components you have, up to some point the engagement increases. But if the number of components increases dramatically, then this means there are too many disjoint ones, right? The engagement starts gradually dropping. So number of posts, engagement with, I think this was in Facebook, maybe number of posts or shares. We have to look at the details.
Whether they invite you when you send, so when they sign in, they were looking at the number of people
who joined the group event. Yes, I think there are Facebook events, and then how many of them respond to join in.
When you give your mailing, when you give your list of emails, you send an invite. So this is before you join. So if many people...
When they join at first, do they continue to be using the site after they join based on their initial friend group, was the pattern.
Okay. All right. So this is, you can see that studying some structural properties of the subnetworks, like ego networks, you can find some normal user behavior, expected behavior. Okay. So let's move on to some attributed subgraph patterns. So given here, an attributed graph will be a graph with some labels on the nodes, and subdu is a method proposed by Noble and Cook that finds subgraphs that are frequent that will compress the graph really well. So you can use the minimum description length principle or encoding principle to find such subgraphs such that the subgraph should be sufficiently small, and using it, the graph should be compressed really well. So description length of the graph, using S to compress it, plus the size of S should be as minimum as possible. Okay, so here in this example, the graph is this entire thing, and AB is a frequent pattern here that compresses the graph really well. So again, attributed graphs here, Macaulay and Leskovich, given a graph, in this case they study ego network, so ego is the here, and these are all the neighbors and their connections among them. The interest is to find communities, that these communities can be overlapping, as in here, right, or nested, as in the blue case. So let's look at an example here. The node features, the nodes also have some features, for instance, name, last name, nationality, and where they studied and where they worked, and so on. So in order to, given an EgoNet, the goal is to find these structures, the clusters. So here the modeling is that each edge in the EgoNet is modeled as a probability. That's a function exponent to the dot product of, so each cluster here is represented by a weight vector. Okay, so here the edges inside, so this edge for the clusters that it belongs to, remember that an edge can belong to multiple clusters due to overlap. The weighted similarity of the n nodes, summed over all the clusters that edge belongs to, should be much larger than all the clusters that it doesn't belong to. Basically says that find the latent clusters as well as the weight vectors for these clusters, such that this edge is more representative for these clusters that it belongs to than the others. So the goal is to alternatingly find these weight vectors and the clusters. Okay, more patterns in graphs. So given a graph, we can also think about it as an adjacency matrix, as Alex introduced. So given this adjacency matrix, how do we carefully reorganize its rows and columns so we go from here to here, right? So you're seeing the runtime running of an algorithm here. The end goal is to find a few blocks that describes the data really well, in the sense that the blocks should be super homogeneous, either majority 0 or majority 1. So again, they use a minimum description length principle that tries to find fewer clusters that describe the data really well. Okay, so here's an example of an outcome. You're seeing the rows are grants and the columns are the keywords, and each edge here is whether this grant is using this keyword. After running cross associations, you can find very sparse and very dense blocks. For instance, we can look at the words that correspond to these clusters, like meetings, organization, session, participating. So there is this coherence of maybe topic associated with these grants, this set of grants that use these. So you can find some patterns of topics and correlated grants to each other. You can do this jointly for attributed graphs. So when you have the graph, you have the adjacency matrix as before, but what about features? Maybe you know these guys like music, these guys like movies. So people versus features, and again, there's a one if that person exhibits that feature, and then you can jointly do this such that, do this meaning shuffle the rows and columns meaningfully such that you get very dense or very sparse blocks, right? Such that these groups of people exhibit these features cohesively. So we call them cohesive clusters. Not only they are dense, but they also share these subset of attributes. All right? So this is joint co-clustering. Moving to using co-clustering for prediction. Here, we are interested in not node attributes, but edge attributes. So Beutel, Ahmed, and Smola is going to use co-clustering to do prediction for the missing ratings. How to do this? So the general idea is to do co-clustering in a sequential way. So at the higher level, you maybe split your users into females and males. Of course, you don't know this. These are latent. You don't know the features, but you are interested in finding these general big blocks of coherence. So maybe all these females, and when the movie is a romance movie, then on average the rating is 3.4, right? And then you can subtract this one, and on the remaining graph you can do the same at a lower resolution. So maybe now you want to split the females into by age, and then the romance movie is by their rating, right? And then these will be deltas. So on average, this is the rating, and then this will be the delta, and when you sum them up, you'll do a good job in predicting. So you can keep increasing the resolution, and the more you do this, the better prediction you'll get, but the risk is that you're going to be overfitting the data. But this is using co-clustering for predictions in the edge-attributed graphs. And the more you keep doing this to increase the resolution, then the more space you need, because you're doing co-clustering on every one. And this graph is showing you how the error drops as you increase your resolution, right? And you can see that even with very few steps of doing this, you can get a very good accuracy. Okay. So far, I told you about finding patterns in edge-attributed, node-attributed, or unattributed graphs for normal behavior. At this point, I would like to ask if you have any questions thus far. Yes, please. Yes.
Any difference from decision tree? It looks like, okay,
So I think in like regression trees here, so we are trying to predict a scalar. So I think the difference is that Alex can give you more details after. So my understanding would be in decision trees, you're splitting the data and then you're doing regression right away at the leaves. Right? Whereas here, you're really at every step gives you more and more information into doing your prediction. So this gives you the average for females and romance movies, and then this is the delta, and then maybe if you keep going through the resolution, you'll get more and more deltas, and when you sum them up, you get the good prediction. Alex?
Yeah, so 2 parts on that. One is that it doesn't work out to be a tree, because the splitting could happen in a sort of much more extreme way. So you have very few clusters per level, but you can move between all clusters. There's no sort of tree-like pattern. The other big aspect is that a tree, generally you think of it as like just individual points, whereas here, because it's co-clustering, it's both the rows and the columns being jointly clustered. So doing that in a tree-like pattern would also be kind of difficult for a matrix structure.
I have a further question. So, okay, in that case, what's the difference between this one and classification with association rules?
Association rules.
Yes.
Yeah, I'd say that's similar in terms of finding these dense structures, right? Like cross associations, co-clustering are all sort of finding these blocks. Similar cross association rules, just sort of the way in which you do the learning changes. And this way, it's a global partitioning as compared to maybe finding a locally dense subgraph.
Okay, maybe another quick question, and then we'll move on. Okay, so let me move on with abnormal. How can we use subgraph analysis to find abnormalities and fraud in real graphs? Okay, so let's start with this. One of the earliest works in 2001, Cortez et al. They studied telecom fraud. So in this case, you're given a node, and you're asking whether this person is committing telecom fraud or not. This is a telecom network. This is who calls whom. All right? Thank you. The way they are going to address this problem is by defining what is called a COI, Community of Interest. And this is known as the top K connections for that person, for that ego. And top K, it can be in terms of number of phone calls, right? In this example, the edge weights are the number of phone calls between these 2 people, and the top three connections would be these with the largest 3 weights, right? So this will define the neighborhood or the association of this person. And then you can keep doing this by not one hop, as in the ego network, but more hops, right? You can go one more hop, and in this case, you're seeing the second hop neighbors. And you can define this as the COI for two-step COI of this person. And these will be the COIs of the neighbors, right? So this is, again, some sort of a recursive approach, but they stop at d equals 2 for scalability reasons. And then you can look at how many nodes in this COI are known to be fraudulent. So there are some known labels a priori. You know that these nodes are committed telecom fraud. And if this fraction is really large, then you say that this person will be also a fraudster. And this is known as guilt by association through the subgraph analysis. In this plot, they show that the fraction of new cases labeled as fraud increases by the number of nodes in the COI that are already labeled as fraud. So this is a good indication. This subgraph is a good representation of the association by guilt. And there will be more. Christos will talk about this in the next section about guilt by association and other global approaches to find fraud through association. Right? Okay. So moving on to another work. In this case, remember the patterns that we found in ego networks using pairs of features and correlating them. Well, we can use these patterns. Remember, anomalies are deviations from the normal behavior. So in this case, the normal behavior is really the fit to the majority of the green nodes here. And then we can measure the deviation from this fit. And here I'm showing some anomalies over here that you see they're all lie on this upper bound, right? That means that they're very click-like. And looking at these 30, 35 nodes, we see that it's actually a full click. All these nodes are within a click. And this is a person creating these template websites about movie reviews and then citing himself, maybe to boost his page rank, right? You create 35 copies of your website and cite yourself, and maybe you're trying to do something suspicious. Okay. In their work, Li, Xiong, and Liu, they looked at modeling fraud directly to find trading fraud. So the way they approach the problem is they first say, okay, how does trading fraud work? Maybe 4 people come together. First, they buy a lot of stocks, right? They just import a lot of stocks. There will be a lot of large in weight in degree. and then they trade among themselves, right, to increase the price value of the stock. And then once the value increases, they'll just sell out everything. So at the beginning, you see a lot of buy-in. So there'll be a lot of large in-weight. In-weight will be really large. And they call this the black hole pattern. And then and trade among themselves, once the price increases, they sell out. And that is going to be a pattern where the outweight is really large, right? And this they call the volcano pattern. So now that you know how fraud works, or how, given this model of fraud, you can go to the large graph and look for these patterns that you defined, right? So that's their approach. Okay. Moving on to intrusion detection. A few years ago at KDD, the problem of looking into intrusion through community analysis was done by Ding et al. So the way they approach the problem is they create a bipartite network of IP, who connects to whom, source and destination. Then they project the IPs, the sources, so they assume that the sources are going to be the fraudulent or the ones that are trying to intrude. They're going to create one mode of the graph. So they project these nodes, they connect each IP, each source IP to each other if they share at least one destination IP. So that's called the one mode projected graph. And then they find communities within this projected graph. So in this case, you see two communities. And they define something as intrusive if an edge, in particular, is intrusive, a connection, if it crosses community boundaries. They call this antisocial behavior. So social behavior is within your group. If you cross community boundaries, then that is something suspicious. Okay, so this is, again, fraud analysis or intrusion detection through a subgraph analysis. So far, I told you about subgraph analysis for fraud detection, in particular for graphs for which there were no edge or node attributes, just plain graphs, right? Just nodes and edges, directed or undirected. So let's move on to a section where we have graphs, but also we have either a lot of node attributes or edge attributes. Okay, so these are more complex graphs. Any questions so far about the fraud in this part? Yes.
A couple of slides there, top K
yes.
nodes. Is there related with the degree of the nodes?
It's related with the weight. So let's look at this node. He has 5 neighbors, and the weight is the number of communications. How many times this person called this other person? So the top K connections are the most frequent because he called these 3 people more. They are their main connections. You ignore the rest. Strongest connection, exactly. And K is a parameter of the model. Yes?
Can you comment on, like in real-world applications, these edges and weights may change over time, so how the temporal aspect plays into these?
Very good question. So this one actually relates, this would be a good transition for the second part, where time can be represented as an edge attribute, and I'll talk about some methods that use time to detect fraud as well. For your particular question of how we extend these methods, so far all these methods are proposed for static graphs, so we have to think about how to extend them for dynamic.
Also, that first one, like the top K, for example, they usually do that on a sliding window, right? So they do use time, but they sort of just take a snapshot of the graph.
Right, window-based. And probably they recompute everything for every window rather than maybe some update. But mainly they are for static case. Okay, so I'm going to move on to maybe more questions.
One other question. So, what you've shown so far assume a lot of tuning parameter settings, the thresholds and the like. How do you choose the best in the graphical?
So for instance, K for top K analysis. If you have some labels, of course, you can do cross-validation for this. Oftentimes, in the anomaly domain, we don't have it. So some extreme case analysis maybe use different Ks and pick the maximum score that you get from different Ks. For instance, this is related to ensembles in anomalies. So for outlier detection, let's say nearest neighbor-based outlier detection, you have to define how many nearest neighbors distance you're going to look at, right? K nearest neighbor distance. So what people do is use different Ks and then pick the maximum score. So what is the worst case scenario that you're an outlier? At what K, right? So you do it for multiple Ks, pick the max value, that will be your score. So it's sort of an ensemble-based approach for anomaly detection. But it's challenging, and especially when there's no labels, we can't do cross-validation. But that's the approach. It becomes an ensemble approach. Okay? Okay, so let me move on to, we can discuss more in detail. I'll have to move due to time. All right, So in the next section, as I said, I'm going to talk about graphs with node or edge attributes. So they're going to be more complex graphs. And the type of fraud you'll see will be more complex. So let's start with Gupta et al.'s work for detecting anomalous subgraphs in attributed graphs. So in this case, you have a subgraph like this where nodes are labeled by their attribute. For example, an orange one is a person working in theory versus blue one is a data mining. Okay? So the way they define an anomaly is you see examples here. A normal one is a set of nodes who are on all data mining and all their neighbors are also data mining. So they live in this cohesive, comfortable area in the graph, right? Whereas these people are living a bit on the edge, right? So they are all data mining, but all their neighbors are theory. So somewhat they are in the boundary of data mining. Whereas here, the reason this is anomalous is that these are a group of people, but they are not all data mining. So they're a mixture of people maybe collaborating from different fields, which is still not something that you would expect. So this is how you model the anomaly. Okay. So now how can we find such definitions of anomaly? The way to approach this problem is looking at the pairs. So given a subgraph like this, okay, for each connected pair, we are going to create a new instance in our data where we will create a vector that is the difference between the feature vectors of these two nodes. So imagine that each node has a vector of features, and then this will be basically the subtraction of those two vectors. Okay, so you do this for all connected pairs inside the subgraph. Then for disconnected pairs, for each disconnected pair, you create other instances. And again, the instance is the difference between their feature vectors. So then the goal, now that you created sort of a connected pairs versus disconnected pairs, sort of a labeled instance, you try to learn a weight vector, right, that separates these two groups with the largest margin. So what does this mean? So the weighted dot product, right, of these vectors should be really small towards this side and should be really large. What does this mean? Remember that the vectors are the difference between the feature vectors of these pairs. So for connected pairs, you want to make sure that their dissimilarity, right, dot product W, the weight vector times the difference of their vectors, the dissimilarity, that's exactly dissimilarity, should be really small, right? Connected pairs dissimilarity should be really small, but in opposite, the dissimilarity of disconnected nodes should be really large, right? And then the learned weight vector will give you the importance of the features to achieve this. And from then onwards, you can compute and whether this graph is anomalous or not by looking at the margin. Right? If the margin is really large, then you can separate these two. So it's a normal graph. If you can't, then it's an anomaly. All right? So it's inspired by SVM-based approach, and the modeling is very nice. This is in the query setup. So anomaly detection is sometimes unsupervised, sometimes query-based, and so on. In this case, you have a graph, and somebody gives a subgraph query, like a triangle. Imagine it's a subgraph pattern. And then you find the matches of the subgraph, all right? And then look at their neighborhood. These are the subgraph matches that you look. For each one, you do this separately. You solve this optimization problem separately. And then maybe sort all these matches and report top K, all right? This is the framework. Okay. Other works that finds outliers in attributed graphs. Again, the same setting. You have a graph. You have node attributes. Each node is associated with a vector of features. So the goal here is to find clusters, dense subgraphs, where nodes within the cluster are densely connected and also cohesive in some subset of the attributes. Right? This is defined as the normal behavior. So you see that these people are densely connected, and what makes these people click, what makes them friends? Well, the fact that they have PhD degrees and they all live in New York City, right? The other attributes are not consistent, so these cannot be what makes them click. So once you can find this subset of attributes and such clusters, you can find an outlier as somebody that is in the cluster but doesn't fit with respect to what is called focus attributes, the subset of attributes that make them click, right? All right, so the way to approach this problem is, this is also in a query-based setting, by the way. So somebody actually, a priori, we don't know what these features are, right? What subspace actually makes them similar. So in order to gauge this, the user gives examples of nodes inside the graph that he thinks are similar. And using distance metric learning, you can find a subspace that makes these pairs really similar, whereas maybe other random pairs dissimilar. So this subspace is called the focus attributes. And then, for instance, in this large feature vector, maybe age, gender, and location makes them really similar. And then you go back to the graph, find clusters, and then the outliers will be that those nodes that belong to the clusters but differ in their sub-attributes. So I'm going to skip this detail of how to do this in more detail, but show an example which is more interesting to analyze. This is a detected focused cluster in a blog network. So each node is a blogger. The edges are which blogger cites what other blogger. So this is a dense group of bloggers citing each other. And the features, the attribute vectors, are the words and frequencies, the word frequencies that they use. For this cluster, we found that, for instance, these keywords, these three particular keywords and sizes by the weight, like the importance of that feature to define this cluster, is this. And the outlier is this blogger. So Voss is a journalist, okay, talking about conflicts in Bush administration or criticizes Bush administration a lot. And all these bloggers were talking about him all the time with high frequency, whereas this person never mentioned him in his things. So he belongs to the cluster. He cites other bloggers in this cluster, but never doesn't fit with their interest at this point. Okay. All right. Moving on, other attributed subgraph anomalies. So these authors, Lee et al. At UCSB, their observation is the following. Given any data, the concentration of attribute will be local, right? So the density of the attribute will be kind of skewed. For instance, if you look at the map of the US, the crime rates will be concentrated in different areas, right? It won't be uniform. And so you can think of this to be happening in graphs too. Given a graph where attribute is probably people who like comedies versus action movies, you may find regions of people inside the graph that are really highly concentrated in comedy liking, right? So then the goal is to really, given a graph, find with node attributes, in this case I look at binary attribute, like or not like, find concentrated areas that are substantially different from the rest, right? That attribute is very concentrated there. So to approach this problem, they take a probabilistic approach. They model two generative processes, one creating the anomaly distribution, one the background distribution, and then model the entire data as an overall mixture. So for each node, the probability of that node is proportional to the sum of two terms. This one is the anomaly component. I mean, K01, P0 is anomaly component, P1 is the background normal component, and this is the mixture parameter, right? That is to be inferred. And then you can, so this component is a Bernoulli variable, and you can write the log likelihood as the sum over all the nodes. And they introduce some network regularizers such that the nodes that belong to anomaly community are cohesively connected to each other, right? There is some smoothness over the graph, so that term is for that. This one you don't need to worry about so much, but this is the overall objective function to optimize. And they solve this using some EM-like algorithm such that to find the anomalous component and the background component, right? Okay. In another approach, by the same group of authors, they took a completely different approach, potentially for the same problem, right? You're given a graph, some nodes like comedy, the others don't. Find me dense regions of comedy-liking people. Same problem, but the approach is a bit different. But what is the output? So the goal is to really elevate some nodes by their proximity to the black nodes. And then once you do the elevation, you can think of the graph as some node elevating, right? A third dimension would be elevation by similarity or closeness to the black nodes. And then when you define thresholds, right, you can find islands, basically, of concentrated areas. So at this threshold, this is one, they call them iceberg, graph icebergs. So this is one iceberg, maybe at another threshold, you'll hit another iceberg. See, these nodes are concentrated around black, these are also, right? The way to do it is a random walk-based approach. What happens is that, in this case, you can do forward propagation or backward propagation. For each node U, you compute the PU, the personalized PageRank vector for node U, and then you look at the indices of the black nodes and sum these things to compute its score. So this will give you the proximity to the black nodes, right? PageRank is used for finding, personalized PageRank is used for proximity finding. This is forward way. The other way you can do is for each black node, you can compute their vectors, personalized PageRank vectors, and look at the youth index and sum these values. And these two things are correlated. You just need to do some normalization based on some degrees. But you can do it both ways. They're equivalent approaches. And they give fast ways to do it both ways. And maybe you can guess that this is faster, right? Because here you just need to compute the PageRank vectors of the black nodes, not the white ones. But they've proposed fast approaches for both. And then you compute these scores, proximity scores to the black nodes for all nodes, define your threshold. Maybe at 0.5, this is the connected iceberg, okay? But bottom line is, given a graph with black and white nodes, the goal is to find concentrated areas of black nodes. This would be the anomaly. Okay, so this far I told you about anomalies in node attributed graphs. Any quick questions? I will continue with edge attributed graphs, some anomalies in edge attributed graphs in the next 15 minutes. All right. So in their work, Beutel et al. Again looked at some anomalies in edge attributes where the edge attribute is time. So in this case, you have users, you have some pages, and like relations on Facebook, right? So one thing you can realize is that there are two dense groups here, right? These users like these pages a lot, and these users like these pages a lot. So it looks like there are some patterns here, but which are all these patterns, are both of these clusters normal? How can we tell which one, if any one of them is fraudulent? And the way to answer this question, they look at time. So when you integrate this additional information of time, what you see is that these people liking these pages can be liking them at arbitrary times, but these people are very concentrated. They like this page all at once, at the same time. Maybe 10 minutes later, they like this one. Right? Very concentrated within time. So maybe they're working together to promote these pages, and they are working within a very limited amount of time. Right? So when you integrate time, all of a sudden you realize that maybe this is not a cluster similar to this one. And in matrix terms, this is the matrix where now color indicates time. All right, the more similar the color of two edges, the more close by they are in time. Okay, and when you carefully reorder these rows and columns, you find these dense regions. Okay, yes, dense regions are clusters, but look at the time. Like there are many edges that are concentrated in time, right? And then given this they call this the lockstep behavior because they behave synchronously a lot in short amount of time. And a formulation is find dense regions tiles of size n and m that performed all these relations in very short time, delta t, and rho is a density parameter. Okay, so then they proposed fast algorithms to do this. And here are some results that shows that it's a stochastic algorithm, so every time you run, you may hit a different solution, different cluster. You find different suspicious behavior in cluster, and but there's a diminishing return pattern, right? Within a few runs, you find a lot of bad guys, right? And a post-analysis, a very interesting post-analysis, shows that, in fact, as opposed to maybe belief that fraudsters create new accounts and then they commit spam, they found that most of these accounts are actually compromised. So, and in different ways, a large majority. So that's a nice finding. Follow-up to this work is work by Chao et al. In similar lockstep behavior footprints, analyzing lockstep behavior footprints, where you have these accounts, and this is time, right? They are performing actions that are really synchronized in lockstep behavior. So this is how fraudsters behave, right? Within this short amount of time, they do all the same actions. Color is, let's think, is action, like logging in or posting a picture or sharing a link, right? You see how synchronized all these accounts are, whereas normal behavior is like this. There's no particular pattern. So now, how could we detect such things? The way they do it is, again, another example here is that here, this is time again, accounts. This is for one action, uploading spammy photos, and the color indicates IP addresses. So you see that within this time window, all these accounts were logging in from this IP, maybe during work hours. They went home, they were logging from this IP again, but doing the same action, right? So super synchronized. And for normal users, there is no such thing. So to detect such things, for each node, for each account, they look at some features, attributes like time, IP address, action that they perform, and they define a similarity function, and they connect two nodes if they perform if their similarity is really high. And then the goal is to, given this graph of similarity graph, find dense regions, like densely connected, heavy subgraphs. Okay. Here are some results on Facebook for different types of actions. you can see that the precision is really large. So whenever you find these dense and heavy subgraphs inside a similarity graph defined by them as previously, whatever they find will be highly suspicious. So precision is high. Recall, we usually don't know, but precision is super high. All right. Continuing, so this is work by Papalexas over here and colleagues trying to find network fraud in bipartite graphs. So here again, you're trying to find network intrusion or fraud. These are sources, these are destinations, but this is not the end of the story, right? We're going to look at some attributes, add some more information, such as the type of connection, for example. That may be a binary categorical attribute, or numerical, such as round trip time for this connection, number of requests between these two, and so on. Right? You add more information, make the graph more complex. Now, what's an anomaly? They're going to use co-clustering to find dense regions in this graph that are coherent in these attributes, binary or categorical, binary or numerical. In this case, you're seeing this two sources attacking these three destinations, maybe with many requests and within a very short time, right? That may correspond to that kind of pattern. But the goal is to find cohesive in not only structure, but also in attributes. And here are some results. Whenever they find such structure, what they observe is either it's fully normal, right? All the nodes are either normal or fully abnormal. So every coherent graph will be either very normal or abnormal. So maybe you can do some post-analysis. In this case, they had labels to do this, but you can also do maybe post-analysis to decide which cohesive clusters are fraud and which ones are not. Okay, so this concludes the second part of fraud detection or anomaly detection in edge-attributed graphs. So in summary, you see here that I talked about anomalies in plain graphs, no attributes, anomalies in node-attributed graphs for these works, and anomalies in edge-attributed graphs. All these papers I talked about, you can find the citations on the tutorial webpage. All right, and this I'm not going to go through. I will hand it over to Christos. Oh, maybe can I take questions anytime? Okay, maybe any questions at the end? Yes.
You had this example in which you were looking at similarity between nodes, including the time feature.
Mm-hmm.
But is there were you upweight when were they weighting this time? So how do they know that it's time related and not other feature related? Because you have time and other features.
Oh, not this work?
No,
hold on.
For the edition, yeah.
Oh, okay. Yes, I think here the similarity function is aggregating everything, right? You don't know whether the similarity is due to time or due to IP. So it's an aggregated function. It becomes a scalar. But the more things you share, the larger the weight will be. And so maybe you can gauge something from the magnitude of the weight.
Yeah, there's sets of actions, right? And each action is the action Pagerank was taken by and the time that it was taken by for that account. You have sets of accounts that overlap in lots of those criteria over lots of actions. That makes the edge way larger. They just have a way of aggregating that knowledge to create that edge.
Yes.
In the black holes and volcanoes approach, do you use the nodes that become anomalies are the ones that are black holes and then they turn into volcanoes, or both?
I think in their analysis, they didn't know whether their data, given a snapshot of the data, you can have both, right? You don't know. So they were looking for both simultaneously. I don't think that given a black hole they tracked it over time because they just had a snapshot of the data at the time. But that's a good point. Like you can do this to verify. Okay. So, Christos.
Great. Thank you very much. We'll continue with the second part of the presentation. And as we mentioned, this will be global methods that are using propagation. And following the layout that Alex mentioned, first we'll give the background, classic algorithms like PageRank and hits, then how we can spot normal behavior and how we can spot abnormal behavior. Again, please raise your hand if there are questions. So one of the motivating question is, given a graph, which nodes are important? And the big motivation, of course, was the web, right? Given hyperlink pages, which pages are the most important in a graph? And there are two solutions that stood the test of time. The first is hits by John Kleinberg. and the second is PageRank. So let's see hits first. The idea is that we have a directed graph. This page, my page points to your page points to some other page, and so on. So for every page, we want to have two scores. How good of an authority it is, which means how many pages point to it. And the second score is how good of a hub it is. Maybe it is not, this page is not very good for what is the query, let's say Linux, right? Maybe this page does not have a lot of information about Linux itself, but it points to so many good pages about Linux that it has a good hubness score. So the question is, how can we compute the authoritative and how the hubness score for every page? The informal definition is that your page is a good hub if it points to good authorities, and your page is a good authority if good hubs point to it, right? So this is a circular definition. Normally, circular definitions don't make sense, right? A cow is an animal whose mother is a cow, right? We didn't define anything, right? But here it does make sense thanks to the magic of singular value decomposition. So let's see the details. Sorry for the equations, right? So it says that the authoritativeness of page Q is the sum of hubness of its incoming edges, right? Which makes sense. You're a good authority on Linux or whatever was the query if a lot of good hubs on Linux point to you. And you're a good hub, page P is a good hub if it points to a lot of good authoritative page Q, right? It's not obvious, but this is a matrix vector multiplication here. You can imagine the authoritativeness score for all the pages, all the million pages, the hubness score for all the million pages, and there is a matrix buried here, says find your neighbors, this is the adjacency matrix. So eventually, matrix vector multiplication several times eventually gives you the authoritativeness scores and the hubness scores. And it turns out that authoritativeness, let me go to the next foil. So if this is our adjacency matrix, 1 million pages pointing to 1 million pages, right? It's not a symmetric matrix, it's a directed graph, right? If we do the singular value decomposition and keep only the first vectors, right? Then the left singular vector will point to have good authorities, good hubs, and the first right vector will have good authorities. And this is what PageRank is doing. Thanks to the equations before, we can apply them many times, they will converge, right? Thanks to the Frobenius-Perron theorem, and eventually we'll get the scores. So singular value decomposition is a powerful tool that Alex will mention it later under factorizations. It's a special type of factorization, but it's the idea behind the hits algorithm. And here are the results. If we're looking for important pages, Kleinberg in his classic paper in 1999, if we look for the word censorship, then the most important pages are the EFF.org, Electronic Frontier Foundation, right? By Richard Stallman and so on. The Blue Ribbon page, CDT, Center for Democracy and Technology, it makes sense. The second method that changed the world is PageRank by Sergey Brin and Larry Page. The idea, first we'll show the simplified PageRank, which says if you have pages pointing to each other, do a random walk. Start from a random page, walk around, and figure out the steady state probability. Whichever page you find more traveler more often, this is the most important page, right? Because this means that a lot of incoming edges are there. Right. So how we do the random walk? The obvious way. If we find ourselves here, there are two outgoing edges, flip a coin, 50% to go to that node, 50% probability to go to this node, and you continue the walk, right? This is the equation this is a vector. For every page Q, we have a rank. For every page P, we recompute the rank. And this says that the rank of page P is the rank of its incoming edges appropriately modulated, right? So this is, as we'll see later, this is related to importance propagation. If this page is important, whatever it points to, get a little bit of its importance and so on. These are the equations. We won't go into the full details, right? A prime is the column normalized adjacency matrix transposed. And eventually, if we stay as is, then this is a vector of 1 oops. Oh, it works. Ha, okay. Right, so technology at best, yeah. So we're going backwards, yes. Right. So this is a vector, and this is the equation for Pagerank. Some people call it the Maxwell equation for the web, right? But this is what it means. We have the vector of all the page ranks for all the nodes. You have 1 million nodes, right? And this is an iterative equation. This is the adjacency matrix, column normalized and transposed. Prime stands for transposed. And this is a vector full of ones. 1 million nodes, 1 million entries, all of them ones. C is the fly-out probability. C is the sticky probability. 1 minus C is the stay-out probability. So the actual page rank says that do the random walk, but whenever and at every point of time, flip a coin with probability C. If the coin says yes, you stay and you continue the random walk. Otherwise, you fly out and you fly to a random node. So this is the vector that tells you where you should fly out. With probability 1 over n, you can fly out to any of the other nodes, right? So this is random walk with restarts. Why this was done? For philosophical reasons, because people don't do random walks, right? We search for Linux, you find a few pages, and then we fly out, right? Then we get hungry and we look for restaurants, right? So we fly out to another place, right? The mathematical reason to do that is to make sure that this matrix, that the eventual matrix always converges, because there is a very, very subtle point. In the simplified version, if a node is a dead end, then we are stuck there, right? It says follow the outgoing edges. If a node has no outgoing edges, what do we do? It doesn't say. The full algorithm, the actual PageRank, says if you hit a dead end, then fly out, right? Pick any random node from the 1 million nodes, including yourself, including the dead end node, and fly out one of them. If we do that with flyouts, then the algorithm always converges. There is the Frobenius-Perron theorem, which says this is an ergodic matrix. No need to go over the details. The algorithm converges, and it always gives you scores. And this is clearly a fixed point, right? The same matrix, the same vector here. We update it, and we get a new vector. After a few iterations, it converges to a fixed point. So this is exactly PageRank with random walks and restarts. And this is what it's doing. We start from here, we move back, then fly out, right? Where do we fly out? Wherever one of the million nodes. Let's suppose we have to fly out from here. Okay, move, follow the edges. The coin says we have to fly out. Okay, fly out, go to another node, and continue. The steady state probability of this random surfer gives you the page rank, gives you the most important nodes, visits the most important nodes most often. And there is a connection. Fixed points are connected to eigenvectors, and which are also related to singular vectors. So in all these cases, we have singular vectors, eigenvectors, and fixed points. So this is the random walk with restarts. This is the output. If we ask, that was 98, milestone paper in that era, right? If we ask for the more important nodes, the font is not big, but the most important node is download Netscape software. Some of us with gray hair remember that Netscape was the ruling browser back then, right? W3 is also an important organization. Welcome to Netscape is the third most important node, so it makes sense. This algorithm makes sense. So, following the pattern that we had before, right? So hits operates on graphs that are directed. There are no node attributes, no edge attributes, and no seed labels. We know nothing, right? PageRank is the same. Seed labels the algorithm we presented has no seed labels, but as we'll see later, we can have the so-called personalized PageRank by Taher Hawelivala, and we could have preferred labels. Let's see the label propagation algorithms, which are also very powerful, and it's the focus of this part. So label propagation, backtrack. Label propagation says now we have some seed labels. Some domain expert says I know that this node is blue, liberal. I know that this node is red, conservative, right? So liberals are blue or 0, conservatives are 1 or red, everybody in between, everybody's in between, right? If your score is 0.5, then means you are independent, you're in the middle. And for these nodes, we don't know the political affiliation. What can we guess? The belief propagation says if we have homophily, right, birds of a feather flock together, as they say, right, then we should suspect that this person has 2 blue friends and 1 unknown friend. So probably this should be light blue, right? We said blue is close to 0, okay, so 0.1, 0.2, right? By the same token, this person should probably be reddish, right? So how do we have an algorithm which will assign scores to the question mark nodes? So Pagerank is importance propagation. If you're important, your friends get a little bit of your importance. This is label propagation. If you're conservative, then your friends are probably conservative. And this is a very general setting with a lot of variations. We'll see some of the main ideas there. Again, feel free to stop anytime, right? So, yeah.
So with the label propagation, so for example, you assign the unknown node a bluish score, and then does the 4th node get assigned another bluish score because the 3rd node that you assigned a blue score to? Like, where do you stop? Because sometimes you're predicting or you're propagating the label, assuming that the 3rd label was right, you assign the 4th label and so on. Like, does that?
Very good question. So let me repeat for recording purposes. So the question is, so this node is blue, right? It probably gets a lot of blue scores. This node we don't know, right? Or actually, a better example is this node, right? This node has a gray neighbor, so the first iteration gets nothing, right? We cannot, right? We don't know nothing in the beginning, and we don't know nothing after the first iteration. In the second iteration, this node will probably become red or reddish, pinkish, right? And then some of these pinks score 0.8, and then in the 3rd iteration, we'll say, since I'm probably red, right, you must be probably red too. So this will become a 0.7. So there is propagation, and the question is, will this converge, right? Yes, and it turns out that for some cases it converges. For some other cases, it's guaranteed to converge. We'll see them in the next foils. But that's a very good question, right? So we repeat the label propagation several times until we reach some sort of convergence if the network converges, right? Answer, that was the question?
Well, part of it. The second part was even if the network converges, how do you know that how do you measure success? Like, how do you know the labels that you assigned to were accurate? Because you started with the fact that you don't know the labels were.
Right. Well, the theoretical way, yes, jumping ahead. The short answer is that we have a function which says minimize whatever labels you find, minimize the disagreement between neighbors, right? So that's the theoretical measure of success. Whether it agrees with reality, then we have to do precision recall and say from whatever the algorithm says this is Republican or right wing, how many of them did we get right, right? That's the question. Yeah. Other questions? Okay, we continue. So for the moment we'll talk about homophily, which means if I'm red, my friends should be red too, or reddish, right? Later we'll see that doesn't have to be the case. We could have heterophily, we could have lots of other types of arrangements. So, more or less answering the question. So, the classic paper on semi-supervised learning is by Jerry Zhu and Zubin Garamani and John Lafferty, which says, sorry for the math, but what it says is that F is the score for node I. So if I'm node I and my score is red, and my neighbor is reddish, then this is good, right? So this tries to minimize the disagreement between neighbors, right? Fi is one neighbor, Fj is the one node, Fj is the neighbor of this node. So the sum of squares of differences of the scores should be minimized, right? Because otherwise there will be a lot of heated political discussions and the people will be unhappy, right? So try to minimize these scores, given that node 1 is definitely red, right? This node is definitely red, this node is definitely red, this node is definitely blue, right? And it turns out that the solution is the right score is the average of your friends. Whatever score eventually you find for everybody, this should be the average of all your one step away neighbors, right? And there is a closed form solution, and this is this makes a lot of sense. There are a lot of variations. One variation studied by Partha Pratim Kumar and Kobe Kramer says that let me backtrack for a moment. So this formulation says that once I'm told that this node is red, score 1, right, in the political spectrum, we'll never change it. Whatever is my final answer after convergence, this node will have always score of 1. This node would always have score of 0. That's it. No budging, right? The next variation says, let's allow a little bit of budging. We were told that this node is 1, but if we see that after all this node has a lot of blue friends, maybe it's not really 1, maybe it's 0.9, right? So if we allow a little bit of variation from the initial conditions, then we have this formulation. I won't go through the details, but this allows for a little bit of doubting what we were given, right? More variations. Again, it's a well-defined optimization problem, right? We have to make sure that neighbors agree, right? You don't have to have friends that are fighting. One is blue, the other is red, and they're fighting, right? We also may have to make sure that we're not too far away from what we were told in the beginning. If we were told that this node is red, we should come up with an answer which is close to red, right? We should not say, oh, this is that blue, right? And this is a regularization term. The details are in the paper, but the main idea is that there is a variation of the algorithm which allows doubting of the initial conditions. More details. A more general setting along the same lines is the so-called pairwise Markov random field. So the mathematical formulation, apologies for all these Greek letters, phis and psis, right? But these are standard in the literature, right? So the probability that node I is blue or red or whatever it is depends on what we believe about node I to begin with. So for this node, we believe this is a red node, so score 1.0, right? And depends on the neighbors, right? So this is what the neighbors of node I, what J is the neighbor of node I, what does the neighbor J tell you believes? So if your neighbors are blue, then you get a lot of blue influence, which tries to counterbalance the red initial belief, right? Why do we multiply? Because there are probabilities. What is Z? Z is normalization factor. Sorry, boring details. It turns out, that's exactly what we said. It turns out that there is an algorithm, the loopy belief propagation, that can help us estimate these scores. The psi here, again, sorry for the letters. This matrix is the compatibility matrix, which says that if you are of type A, red, or Republican, right, then probably your friends with high probability, 0.8 probability, your friends will be red too, right? If you are blue, then with high probability, 0.8, it happened to be the same, it doesn't have to be the same, your friends will also be blue. So this is a compatibility matrix which indicates homophily. Question?
You assume only the highest value. This is kind of fusification of the data set.
I'm sorry, I assume the highest value? Yes.
Probability, you only account for the highest value, or you use both and have kind of fusification of the data set?
The latter. So we use both, right? And there are more complicated cases who might we have 3 types of values, right? Red, blue, and yellow, or city, right? New York, Boston, Sydney, Melbourne, right? So this might be a 4x4 matrix, diagonal if we have homophily, other than diagonal if we don't have homophily, right? So, but we use all the scores. You're right. And we'll see later examples of a 3x3 matrix where it's neither diagonal nor counter-diagonal, right? Okay, so with loopy belief propagation, we can find, usually it converges. There's no proof that it converges, but usually it converges for real data. And it gives the scores we want. It tells you for all the question mark nodes what should be the appropriate score in the range 0 to 1, liberal or conservative, right? How the belief propagation works. Again, lots of letters. This is an assignment statement which says the belief for node I, whether you think this node I should be blue or red, right, should be what you believe initially, what you were told initially. We were told that node I, this node is blue, red, so this should be close to 1, 1.0. And also all the messages that the neighbors, J is a neighbor of I, all the messages that the neighbors are sending to node I, right? So your blue neighbors will send blue messages, your red neighbors will send red messages, you will collect them all, you will multiply with what you initially believed about yourself, and this is the score. This is not an equation, this is an assignment, right? So we'll do it iteratively. The messages, this is a complicated way to say the message is, backtrack. The message is more or less the compatibility matrix. What do I believe about my neighbor? 0.9, so means almost red. I'm neighbor, so 0.9 times 0.8, this is what my neighbor says about me, right? And we would stop there, except that there is the subtle issue that we have to avoid the echo. If I tell you I'm red, in the next iteration you'll tell me I'm red back because I told you I'm red, so you become red, and then you'll tell me back I'm red. So my redness will be amplified unfairly. So this sneaky, this subtle difference says that exclude messages from your previous step neighbors, right? Because they don't give you more information. They just repeat what you told them. Apart from that, the messages make a lot of sense, right? If I'm blue, my neighbor should be bluish. If I'm red, my neighbor should be reddish, right? And that's it. Question? Yes, of course.
Probability matrix, is it also optimized through iterations, or is it given that one?
This matrix? This is given by a domain expert. Very good question, yes. And actually, there are some colleagues which try to estimate the matrix. The paper has not been published yet. Try to estimate the matrix from the given data, right? It's a very tough problem. So for the moment, we bypass the problem and say this is given. That's it, right? And we'll see all the examples we see for belief propagation. The matrix is forced by God, right? Forced by us, and this is it, right? Yes. Right. Okay, other questions? Okay, so, I'm sorry? Oh, very good question. The edge list is fixed, frozen, right? In the typical 99% of the cases.
So my neighbor said does not change.
Correct.
Every time listening to echoes.
Every time you listen to your neighbors and they give you updated information about what they are. So initially, this neighbor will tell you nothing. I'm 50-50, right? So this will send an empty message to node B. Node B is more or less staunch Republican, so of course won't change, right? This node will get a Republican message from here, a conservative message, so will become even more Republican, right? Next iteration, this guy will get a reddish score from this neighbor. So this will pass even less reddish score to the next neighbor, right? So the edge list is frozen, right? If that's what you're asking, yeah. The scores of every node change at every iteration, and hopefully they will reach steady state. And in most practical cases, they do reach steady state. Is that the question, or?
So I was just wondering, like, so there is a flag associated, so that
Flag?
So the idea is that you say no, that there should not be echoes. How do you ensure that there is no echo?
This is the assignment. Very good point. So the question is, this is an assignment, right? So how do we proceed? The idea is that the messages should sum up to 1. Oh, no, I'm sorry. The beliefs should sum up to 1, right? So you believe you are red with score 0.7 and blue with score 0.9. That doesn't make sense. It should sum up to 1, right? So we normalize the beliefs to sum up to 1. So this is this constant. that I didn't mention, and this is estimated for every node. You make sure that the beliefs sum up to 1, right? And then we continue. But the edge list is frozen. Yeah. There was another hand, yes?
In line graphs, the edge is actually probabilistic, and so you have a fully connected assumption, but it's very weak. You don't know whether in fact people are connected or not. How would you approach this in that situation where you have a probability of the edge existing?
So you're saying that this edge might not be there, right? We know that this edge exists, but we're not absolutely sure, right? This edge might exist with probability 0.7. Missing data, erroneous data. The algorithms we mentioned do not handle that. They assume frozen stuff. That's it. This edge exists forever, from now till eternity, right? This edge exists forever, and so on. If it's probabilistic, I'm sure there is work on this, along these lines, but we won't cover it in this tutorial, right? Very good question. Thanks. Anything else? Okay. Yeah, somebody else? No. Okay. So we continue. So the belief, this is the belief propagation, right? This is the assignment statements, as we mentioned. And it turns out that here is the layout, right? We send random walk with restarts, can support homophily. If I'm important, my friends are important, right? Heterophily, we cannot support it. An example of heterophily would be if I'm a talkative person, my friends will be probably silent because otherwise nobody will get time to talk, right? So this is heterophily, right? Random walk with starts cannot support heterophily, right? If I'm important, my friends are important. That's it, right? They cannot, right? Convergence, random walk with starts is guaranteed to converge thanks to the clever trick of the fly out and Frobenius-Perron theorem, right? So it always converges. And scalability is excellent. It's, you do a matrix vector multiplication a few times, and this is it. Sparse matrix vector multiplication, and this is excellent scalability. Semi-supervised learning can support homophily, maybe can support heterophily, right? Talkative people team up with silent people. Convergence is guaranteed, and scalability is very good. Belief propagation can handle homophily. As we'll see, it can handle heterophily and everything else, right? Convergence, sometimes it happens, sometimes it doesn't, right? And scalability is also good because we operate on the edges. So it's linear on the number of edges. We cannot do better than order E, order number of edges. We have to read the matrix, right? So, and again, sorry for the equations, right? But this is the equation for random walk with restarts. If these are the importances, this is a vector of importances we have initially. And for the standard random walk with restart, this vector is full of ones, right? This is the vector of importances after the algorithm runs. And this is the adjacency matrix. This is the diagonal matrix of the degrees. And this identity matrix. So this is a well understood equation. We solve it, we find the scores. These are the scores, a vector of 1 million nodes, right? Semi-supervised learning is more or less the same. Instead of fly out, we have alpha, which is how much we want friends to be similar, right? How much political fights cost, right? And again, we solve this equation. Gaussian belief propagation is exactly semi-supervised learning. We didn't mention what is Gaussian belief propagation, but they're all more or less similar equations. The adjacency matrix, the identity matrix, and do an inversion to solve for the vector x, right? So let's continue with normal behavior and then abnormal behavior. This is a paper by Deepak Chakrabarty and his colleagues. Now suppose we have two types of labels. For every node, we know the school, underlined, and we know the city, italics, that this person lives in. For this node, we know that this person is going to Duke, and he or she is originally from New York. So what can we say about the rest of the nodes, right? For this node, we know that this person is in New York, but we don't know the school. For this person, we know nothing, right? So then the standard belief propagation will say, well, if you are from Duke, then everybody else around you should be from Duke. If you are from New York, everybody else around you should be from New York, right? That makes sense. The key observation is that only one label in social networks, one label is enough to establish an edge. So the algorithm says, flood this network, and apparently if these two are from New York, probably this person is from New York. Probably this person is also from New York, so schools don't matter for the blue curve, right, for the blue, right? For the red one, this is Stanford, probably this is also from Stanford, this guy is from Stanford, so probably, yeah, this guy's in Tokyo, but probably studied in Stanford, right? So here we have the red group which agrees on school, the blue group which agrees on city, and therefore the middle node, our best bet is to assume that this person also went to Stanford to satisfy the red group, but now lives in New York to satisfy the blue group, right? So this is the idea behind the paper by Chakrabarty and colleagues, right? Which is when we have two types of labels, right? We'll skip the math, right? Sigmoid function, and here is the success. This algorithm works well. Higher is better if we have if a person has, if a person has 20 friends, let me see what happens here, right? If there are 20 friends and they agree on the employer, there is small chances that you're also, if 20 of your friends are working for Google, probably you work, maybe you're working for Google. If this is green, if 50 of your friends are working for Google, then almost, 80% you're working for Google. If 100 of your friends are working for Google, then this is a huge score, right? Then there are very high chances you work for Google. And then we have diminishing returns, right? Employer is a very strong signal. College is a weaker signal, right? If you went to Stanford, probably your friends went to Stanford too. Some of your friends went to Stanford, and so on. And let me see, right? And here it says that if 20% of your friends are red is hometown, blue is current city, and so on, if 20% of your friends are from some school, then 90% you are from that school too, and so on. So this is a very strong signal, and it shows that we need to agree. Friendship edges are due to one common attribute is enough to create a friendship edge. Right. Coffee break, 10:30, right? Let's, okay. So we can have questions and then we can go for coffee break. Any questions before? Okay, so next we'll have the coffee break at 11. We'll continue with abnormal behavior and latent factor models. Thank you.
Super fast. No, you were good. Okay, the next 10 minutes. 10 minutes worth of Okay. Oh, you met Alex?
Yeah, so if you add 2 to the end, user behavior